Hello everyone, my name is Arhan Bilici, and in this video I will be presenting you my Physical 102 laboratory project about internal resistances of batteries. Main goal of my experiment is to observe how terminal voltage value of a different type of batteries change under varying current load. By doing so, I will also be analyzing their electrical efficiency and comparing their overall performance. Now let's start by giving some background information about the principles behind this experiment.
In reality, batteries are not perfect due to factors like chemical barriers and internal heating. As shown in the schema, we model a real battery by including its internal resistance. By using this physical model, we transform our formula into a linear equation. This allows us to analyze all the measurements taken throughout the experiment. Now let's move on to the experimental process. Here we have three different brands of batteries. As a start point, we are calculating nominal voltage value for each battery. Calculations show that alkaline battery had 9.58 volt nominal voltage, extra heavy duty battery had 9.72 volt nominal voltage, heavy duty battery had 9.94 volt nominal voltage. To set up the circuit, I start by connecting the battery's positive terminal to the ammeter using alligator clips and banana cables. From the ammeter, the wire leads into the rheostat. Finally, I link the rheostat back to the negative terminal to complete the loop. After setting up, I connect the negative terminal and measure the instantaneous voltage using the voltmeter. Here, I'm adjusting the rheostat to vary the current flowing through the circuit. Once the ammeter reaches the desired value, the rheostat is kept fixed at the position to take the measurement. Here are the tables displaying our experimental data for each type of battery. As you can see, they include the measured voltage and current, along with the efficiency values calculated based on the nominal voltage for each battery. Here is the best fit line for the heavy-duty battery under varied current. Now let's analyze the results of this graph. From the equation of the best fitting line, the internal resistance is 24.17 ohm and the experimental voltage is 9.61 volt. This confirms our nominal voltage value with only a 3.32% error. To continue it, this is the best fitting line for extra heavy duty battery. From the equation of the best fitting line for extra heavy duty battery, we see that internal resistance is 16.52 and the experimental voltage is 9.57. This confirms our nominal voltage value with only a 1.54% error. Finally, this is the best fitting line for alkaline battery. From the equation of the best fitting line, the internal resistance of alkaline battery is 3.64 ohm and the experimental voltage is 9.56 volt. This confirms our nominal voltage value with an incredibly low error of 0.21%. This is the efficiency versus current graph. Blue is alkaline, black is extra heavy duty and red is heavy duty. At low currents, all batteries perform well. However, as current increases, alkaline remains highly efficient while the others' voltage drop rapidly. If we again look at the graph, we notice that it doesn't start at 100% efficiency for each battery. While investigating if this was an experimental error, we found that this was a scientific reality called activation polarization. Activation polarization is the initial energy barrier a battery must overcome to start working. This experiment highlighted this hidden factor that we initially overlooked and turned this experiment into a great learning discovery.
To conclude, we successfully measured and calculated internal resistances of three different types of batteries. By using graphical analysis, we provided empirical data, and analyzing those empirical data, we explored real-world scientific phenomena like activation polarization. With consistent results and all objectives met, this project was a success. Thank you for listening, and thank you for sparing your time.